Okay. Acids and bases. So they are all over the place, right? So there's low pH, means it's really acidic, a lot of hydrogen ions, right? High pH, really basic, a lot of hydroxides in solution, right? We have our pH scale, goes from 0 to 14. I mean, you can't get away from acids. They're even in your body controlling the pH. We have our pH scale. You should notice this if you haven't already. Like, we're used to saying pH 7 is neutral. Well, that's really a hydrogen ion concentration of 10 to the negative 7, right? If you have a pH of 2, that's a 10 to the negative 2 hydrogen ion concentration. So that's our log scale. Okay. So let's start off, though, Naya, with protic. What does protic mean? The substance is protic. What would you say? He doesn't know. Desiree? What would protic mean? Protic. Kind of sounds like proton, Andy. Yeah, it will create. You're pretty close. I guess that works, right? It's going to generate, or it's going to provide the protons, right? So just take one. And then we've got an acid and a base, Melissa, in general. Mix what and what?
Conjugate base and conjugate acid.
I guess you could say that.
H2O and salt.
I guess that works, but what was I shooting for? You can take one. Shooting for salt and water. Yeah. Shooting for salt.
Do I get one?
That wasn't the question. So protic generates protons, or proton supplier. Acid and base. I think I don't know. I think salt and water is what I was really shooting for, but because I'm trying to bring us back from general chemistry up to where we are here. So kind of a little bit of review. And then Melissa did mention this conjugate acid, conjugate base pair thing. Jackie, what is that? Conjugate acid, conjugate base pair. What was this stuff? Do you remember? Okay, conjugate acid, you take away the hydrogen, you get the conjugate base, right? The conjugate base grabs the hydrogen, you get the conjugate acid. So just an equilibrium going on between the two, right? That's pretty much all it was. Okay. For example, Jeff, the conjugate base of HCl is Cl minus. Okay. Now, Jeff, this conjugate base is definitely what? Weak. How did he know that? How did he know that? Because HCl is strong, right? Remember the double arrow thing that Monica likes to hit on, right? And we should be drawing this all the time. But we know that HCl is a strong acid. So that double arrow thing is, dang, it's about as one way as you can get. You can draw the smallest arrow possible going back. Because there isn't a back reaction. It's just so strong. So you think of this HCl, right? The conjugate acid, the conjugate base. So acids doing what acids are supposed to do, protic, creating hydrogen ions, protons. Hydrogen ion is a proton, right? Creating protons in solution. But that means that chloride should react with it, and that's what a base should do and make HCl, but it can't. It's so weak. That's exactly right. Okay. Autoprotolysis of water. Danielle, it's an actual reaction. Autoprotolysis of water. How would you finish that reaction? H plus plus OH minus. Yeah, just what you got. Good. Okay. And then with a K what? How do we express that? Not Ka. It's a Kw, which is equal to, Kimberly, can you finish it? Concentration of hydrogen ion, the hydroxide, all over. Why is it 1? Because it's a liquid. Is there one left for Kimberly? Huh? She got the last one. And it's strawberry, my favorite. Okay. What is pH used for? I don't know. What would you say, Monica? What would you say pH is used for?
To measure the acidity.
Yeah. How acidic is it? I think that's good. What is the equation to calculate pH? Kimberly, what's the equation to calculate pH? pH equals some equation. Negative log of concentration of hydrogen ion. Do you know they call this the P function? You can take P of anything, and it's the negative log of that thing. We call it the P function. So pH would be negative log of hydrogen ion concentration. How about pOH, Ricky? What would be the equation for pOH?
That's a good question.
P function. P function. pOH is the
Oh, yeah, got it. It's a negative log of OH.
negative log of OH. Okay, so there's a couple equations that we should definitely know. All right. You take pH and you add it to pOH, Ida. Now we're talking about water here. This is all referring to the hydrogen ions and the hydroxides in water. This is all referring to water. You take the pH of water, add it to the pOH of water. You should always get what number? Anybody know? What number do you always get? 14. Yeah, 7. Good luck. Good guess, but it's 14. Okay, 7. 14. 7 is neutral pH. Strengths of acids and bases. So referring to their strengths now. What is the difference, Sabina, between a strong acid and a weak acid? Yes, a strong acid dissociates, perfectly said. A strong acid dissociates 100%. Weak acid dissociates, I don't know, depends on what the weak acid is, 1%, a millionth of a percent. Okay. So strong acids, 100%. I guess you could call it like HX goes 100% to H and X minus. Right? That would be a strong acid. Well, how can you tell them apart? How do you know if, for I guess, Kelly, this is where I'm coming from. Let's name me a strong acid, Kelly. What's the name of a strong acid or a formula for a strong acid? HCl. Good one. Okay, so I have 0.08 molar HCl. And the question is, you have 250 milliliters of it. Yeah, let's make this as complicated as possible. You have 250 milliliters of it, and they want to know what's the pH. How do you do this?
Negative log of 0.08.
pH is a negative log of H. pH is a negative log of 0.08. Exactly. What about the 250 mils? It's in the question. Don't we have to use it? Oh, analytical is going to do that to you. They're going to throw in information that you don't need to solve the problem. That's more real life like. So that's how you get the pH, because it dissociates 100%. So if the HCl concentration is 0.08, well then the chloride concentration is 0.08. The hydrogen ion concentration is 0.08 because it dissociates 100%. Okay. Compare that to calculate the pH of a weak acid, and that's coming up. But the point is you can't just do this for a weak acid. So how do you tell in the first place, that's where this is coming from, how do you tell in the first place one from the other, right? Because if it's a strong acid, oh, done. All I gotta do is take the negative log of the concentration or whatever the acid is and I'm done. But not with weak acids. How do you know which problem it is? Did you hear Sabina? If this problem, this acid, it's not one of the 6 strong acids, it's got to be weak. Then you have a whole big problem on your hands. So know these strong acids. Know the names and formulas of the 6 strong acids. And no problem, Desiree knows them all. Desiree, what were those strong acids? Do you remember some of them? HCl. The halogens who gave you half of them. HNO3. Br. H2SO4. 1, 2, 3, 4. 2 more. Remember, the halogens gives you 3. So we have the HCl, we have the HBr, HI. Okay? 1, 2, 3. One more. You want to remember it? HClO4. Okay. See if we can name these here. Oh. What's this one? Hydrochloric. Nitric. Hydrobromic. Sulfuric. Hydroiodic. Perchloric. Right, so know the names and formulas of the 6 strong acids. Again, the reason why is because of what Sabina said. You know these 6, then you know how to do all the easy ones. So then if it's not one of these easy ones, you can calculate you'll have to calculate the pH of weak acids. Calculating the pH in weak acid solutions. Okay. So this is scanned from the back of the book, Appendix G. So they give you the structure of all these acids, and the acids, their acidic proton's always in blue. Then they give you the pKa, okay, and they give you the Ka. Kind of redundant. If you have one, you can get the other one. But okay. So we have these Kas now, and all these acids. And notice these acids are not in the 6. That means they're all what, Andy? All these acids are weak or strong. All these acids they're all weak, definitely all weak. So they give us the equilibrium constant. It has a little subscript on it, just like Kw. Whenever there's a little subscript, you got to write the reaction in the right way. So how do you write these reactions of these acids giving up their proton? Melissa, how do you do this? How do you write a Ka reaction? Like the acid always goes where? On the reactant or product side? Acid's always over here. The acid here going to, right, H plus, and it's, I guess you could call it its conjugate base or something, right? So I think the book likes to use A. Or in general, they like to use A in general. So HA is just in general all my weak acids. It breaks up into H plus and its conjugate base, A minus. Should have a little double arrow going there. Okay. So Jackie, the question comes down to how do you find the pH? They say it's 0.2 molar, like HF. Because HF isn't on the list. So that means it has to be weak. How do you find the pH? Now, this is a hint. Because here's our answer, right? If we could just make a what table? Make an ice table. They're all gone. If you make an ice table, right, there's your answer right there. If you make an ice table. Okay. So let's try it. What's the pH in 0.1 molar acetic acid? So Jeffrey, what do you think we should do for this? Write the reaction. Write the Ka reaction. So HC2H3O2 goes to Danielle. What would be the products? Now we want to, yeah, CH or C2H3O2. Okay. And, right, that's my A minus part, plus, yes. Well, hang on. We want to get it into this format because we want to do ice on it. So this format says HA, H plus plus A minus. Oh, did you guys notice in the first place? It's right here. Because you need this number, right? You need it. So maybe you didn't notice that before we started. They gave us the Ka for acetic acid. So we need to write the Ka reaction for acetic acid. So the only thing we're missing is the H plus, right? And then we have to do ice on it. Got to fill in the table. How would you fill in the table, Monica? Yes. Yeah, the other two, there's nothing there initially. And then the change row, Kimberly? How about that change row? The C. All right. I would assume that changes, things should be decreasing here, and they should be forming over here. Minus X. And for H plus and acetate, it would be yes, plus X and plus X, or just X and X, whatever you like to write there. Then our answers, Ricky, are in the E row at equilibrium concentrations. What would they be?
For acetic acid, it would be 0.1 minus X. The next one would just be X for the hydronium, and then for the A plus.
Yeah, same thing. He mentioned hydronium. All right, H3O plus, it's the same as H plus. Okay. Either we're after getting that X, because if we get the X, that would be the hydrogen ion concentration. Then we just have to do what to it to get the pH? Right? Because we're going to solve for X. We're going to get that number. But is that our answer? They want to know what the pH is. So how would you get the pH? We'll just take the, anybody help her? We're going to go through some work. I'm just jumping ahead to make sure you see the big picture. We're going to get this number, right? We're going to solve for it. We're going to find it. Then when we get it, we're going to substitute it right in there. Take the negative log up and we'll have the pH. So that's kind of the big picture. But the next step in getting that X would be what, Sabina? How would you get that X? Well, not KSP. You're right. It's the same format as KSP. It's Ka now. And the Ka is, oh, I can't even read that. Can you read that in your notes? 1.75 to 10 negative 5. Ooh, do we like that negative 5 number? Right? I like that, because you know what's coming up. And that's going to be what over what, Kelly? You mean the acetate? Divided by acetic acid. All right, so that would be, Gloriana, if we substitute in there, we'd have what? What over what?
X plus X, or X times X.
X times X, all over,
0.1 minus X.
okay, all over 0.1 minus X. Okay. So now if you really are a glutton for punishment and you want exact answers, this is anal chemistry, so you want to be anal and solve for X without doing any approximations. You'd take the 0.1 minus X, move it up here, and multiply through, set up a quadratic equation and all that. But we don't need to do that. Because we're going to do what? Which X? The one on the bottom. Because X has to be extremely small. You take products over reactants, and you got to end up with 10 to the negative 5. So X has to be really, really small. So much easier. So let's solve for your X, figure out what the pH is. Now your answer had better be, Desiree, back to you. Your answer had better be bigger than a pH of 7 or lower than a pH of 7. Which one had it better be? Because this is acetic acid is an acid. So your pH had better be what when you're done with this? Smaller than 7. Right? Otherwise you messed up somewhere. Did you get like a pH of 2.88 or so? Yeah. Excellent. Okay. pH around 2.88. Okay. You okay with this? Danielle, this makes sense? Where did I lose you? Okay, so what I had to do is I had to take that whole thing is equal to 1.75 times 10 to the negative 5. So take this times 0.1, right, and then take the square root, and you'll get that. Take the log of it, negative log of it, 2.88. Yeah, so take it times 0.1, and then you'll have x squared equals that, so you got to take the square root of it. Calculating the pH in weak base solutions. Okay. Man, I should have saved the cheesecake for this one, because this is a good question. Marlena. Give an example of a compound that when you add it to water, it would make the solution basic. In other words, it's a weak base. This is the question. It's kind of like, let me give you the thought, the thinking here. The thinking here is, for example, chloride. You know chloride is a conjugate acid or a conjugate base. It's a conjugate base, right? Its conjugate acid is HCl. So the thinking here is, okay, I can add a cation to this, K+. Add it to water. I just added a conjugate base to water. But it's not really going to work with potassium chloride because chloride is such a horrible base, right? It doesn't do anything. It just sits there. It's like a spectator ion. So this would not be a good example. But that's the thinking. So think of an anion that you can add a cation to, dump it in water, right? So you can make it a salt, dump it in water, and it'll be a basic solution. Andy, can you think of one?
Sodium hydroxide.
Sodium hydroxide. But it wants weak, though. Now that would be strong. Think of the, Melissa, think of the, anybody, think of the anion first. That's how I do this. Think of an anion. And that anion, the trick to this is the anion can't be on what table? The anion can't be here. And this will always work. Think of an anion that's not in this table. It will work. What would be one? Yeah, but that's a strong base. So we can't pick that one. What's that? So we have, I heard fluoride, right? So what would you combine with the fluoride to make it a weak base? Lithium. That sounds good. Pick any cation. And those alkalis are always safe because you know they're going to dissolve, make anything dissolve. There's an example of a compound where you put it in water, it's going to be a weak base solution. What would be another one?
This is baking soda.
Okay, now, yeah, but I'm talking about chemical formulas.
Carbonate.
There you go. That's a great one. There's a couple of them in there. You could pick sodium carbonate. You could pick sodium bicarbonate. Because all of these anions, they're not conjugates to strong acids. They're all going to make weak base solutions. Combine sodium with phosphate, right? Just not sulfate. Or sulfite, SO3, nitrite. All those polyatomic anions that you had to memorize for Gen Chem. There's a lot of weak bases. So solutions of weak bases, you put them in water, put those compounds in water, Jackie, and those solutions are what? Basic, acidic, or neutral? They'd be basic, yeah, they better be pH bigger than 7. So to best describe the equilibrium, Jeff, what reaction should be written? KB. A whole new reaction to write to describe the equilibrium of these weak bases. Not Ka, not Kw, Kb reaction. So how do you write these Kb? Oh, that should be a small b, by the way. How do you write these Kb reactions? Danielle, how do you think we're going to write them? In other words, the weak base product or reactant side? Yeah, where would you put the product? It wants to follow the same format as our Ka. So our Ka, you had your acid, and it does its job. It creates hydrogen ions. The weak base, it doesn't generate hydrogen ions. It generates what? Way up to the beginning here. Here's a basic solution. A base generates what in solution? Hydroxides. So that's the info that a Kb reaction wants to relate. It wants your weak base over here, and it wants hydroxides over here. Okay, hydroxide ions. So how do we write these? I think the best way, the easiest way for me to remember is to stick with one convention. HA is our convention on writing a conjugate acid or a conjugate base? Conjugate acid. So we all agree and we all kind of see that. So the conjugate base would be what? A with a minus. So that's going to be my conjugate base. That's going to be my weak base. Okay. And I'm supposed to generate hydroxides. Now to make this whole thing work, that weak base grabs a proton and makes the conjugate acid, right? Because they both have to be there. Just like in our, right? They're both there. The conjugate acid-base pair are both there. So we need our HA here. So on this side, we've got an H, right, that we're generating, the conjugate acid, an OH. Well, what needs to be over here then? What's missing? Water, H2O, right? Here's your OH and your H. There's your H2O. So our KB reaction is always H2O plus the weak base gives hydroxide and the conjugate acid. So just know that. Know that general format. Okay. Monica, how do we get numerical numbers for KB?
Don't you take the Ka away from, what is it,
Oh, okay. That's one way. She's calculating. For example, acetic acid is HC2H3O2. And here's its Ka. Kw is Ka times Kb. So if I want to find the Kb for acetate, I have to look up the Ka in a table, and I plug it in, and then my Kb would just be Kw all over that Ka that I looked up. So that's how I could get Kb for acetate. So I think that's one way. The other way, I guess we should write that down. One way, Kb is Kw all over Ka. What's Kw? Ka you get from tables, right? What's Kw? Yeah, what was the number? 1 times 10 to the negative 14 is Kw. And Ka you get from a table. Okay. The conjugate acid, right? The other way, the second way, is just use a table in the first place. Sometimes you can get lucky, okay? Especially neutral base, like ammonia, NH3. There's a table somewhere, you just have to find it. Okay, then it comes down to how do you find the pH of a weak base solution? So Kimberly, we have, pick one of those weak bases, sodium carbonate. That's an ugly one. Let's pick this one, sodium bicarbonate. We have 0.3 molar sodium bicarbonate. How are you supposed to find the pH of that solution? Could we take the negative log of this?
Yeah.
Of 0.3?
Yeah.
If, I think we need to back up. What were our strong bases? We kind of, these notes skipped that. I probably shouldn't have. What were all the strong bases? These are the easy ones. These are the ones where they give you the concentration, take the negative log of it, and you've got not the pH, but the POH. But what were the strong bases? All the hydroxides with the alkali metals. Sodium, lithium, potassium hydroxide. All of those guys. And then there were some exceptions to the solubility rules for hydroxides, calcium, strontium, barium. So those are also strong bases. But the idea here is if you have, here's where it's easy, Kimberly. You have the 0.1 molar NaOH. Well, we can't get pH, but we can get POH. POH would be negative log of 0.01, or sorry, 0.1. Right, so we get our answer. And then you get pH from the equation, what relationship? pH plus POH is 14, and that's how you get the pH. Okay, so this is where the easy ones are for bases. Well, we kind of skipped it, sorry. So we skipped the easy stuff. We jumped right into the hard stuff. You have to calculate them. You have to do another ice table for a weak base. You have to do another ice table. Well, if there's an ice table, there has to be a reaction. What reaction are we going to be using? Probably, Ida. The K what reaction? KB. Right. So here it is. We have sodium acetate. What is the pH? Sabina, how can you write that KB reaction? How would you do that? Yeah. And it's nice. See how she left out the sodium? Because it's not going to do anything. It makes it easier. Yeah. Has to be OH. Yeah. You're getting it. And the acetic acid, the conjugate, right? It's conjugate. We're just missing one thing now. Yeah, the H2O. Okay. Great, we've got our reaction. So Kelly, how would you fill in this ice table? Under the acetate. Perfect. Yeah, H2O dashes everywhere. That never shows up. How about on the product side? Yeah, perfect. Okay. Now what, Gloriana? Now what should we do? Yeah, that KB expression would be the word, the KB expression. KB is KW all over KA, which is going to be 1 times 10 to the negative 14 all over Ka. So you have to look up in a table the Ka for acetic acid. So you go dig it up. 1.75 times 10 to the negative 5. And that's equal to x squared all over 0.1 minus x. All right, see if you can get your x. For your x, did you get around 7 times 10 to the negative 6? Okay. Hopefully you'll get that. Now, x is, do I take the negative log of this and get my answer? Or what's the game plan? X is the what? I can't jump that high. X is the hydroxide concentration, right? So the game plan here would be take the take the negative log of this. That's your POH. Subtracted from 14, you'll have pH, right? So the game plan here would be find the POH first. Right? And then you know that pH plus POH is 14. And solve for pH. So I got about 8.88 or so. Something really close to that. Okay. So there's just one last thing to talk about. And there's hardly any homework on this, thank goodness. But the idea here is pretty straightforward, I think. They tell you that there's an acid that gives up more than one proton. So it could be diprotic, triprotic, tetraprotic, whatever. And you can relate all the Kas and Kbs. So, for example, you'd have, for triprotic acid, that means N is 3. So I'm going to write these expressions here. Kw would be Ka 1. So here I is going to be 1. Okay. I is just your little counter. So I'll Ka1 times Kb, right? And Kb what? Well, N is 3. 3 plus 1 is 4. Minus 1 is 3. So Kb 3. Right? And then write I is 2. And write the next expression. Right? Because you have 3 equilibria going on here. I should have a nice... This is what it looks like, right? You have these multiple deprotonations going on. But I is 2. You'd have Kw equals Ka2 times Kb what? 3 plus 1 is 4, minus 2 is 2. So that has to be Kb2. Now I have the last one, I is 3. I'll have Kw equals Ka3. That's the last one, because there's only 3 protons, times Kb, 3 plus 1 minus 3 is Kb1. And there's my 3 equations to relate the two. Okay. So give the homework a shot, come by, and I'll be glad to help you out with these problems.